Strength is very less again. I don't know what's happening. Am I audible, students?
Yes, ma'am. Yes, ma'am.
Okay, okay. Okay, we'll continue with this topic. Yesterday, I gave the introduction to bottom-up parsers. So we know the difference now between the top-down parsing and the bottom-up parsing. The main operations that are involved in bottom-up parsing, they are shift action, reduce action, accept, and error. We will take this example and see how the stack input and how the action is applied. So first, let us start with the stack having a dollar symbol, which is the end of file marker. And let us take the same input, say ID star ID dollar. Dollar is appended to make sure that we terminate properly. Then the first thing is what we do is now we are pointing at the symbol say ID, because always our scanning is from left to right. So we will point towards the first symbol. First thing is that we are going to shift perform the shift operation, because at least one symbol should be there to apply any rule. So by default, the first action will be the shift action only. So let us shift. Shifting means whatever symbol you are pointing to in the input buffer, that will be pushed onto the stack. So it looks like this after shifting ID. And now the content of the buffer will be star ID dollar, and we are pointing at star now. So at this stage, what we can do is we have to find the handle which can be used for substitution. That is, we have to replace our substring by some LHS symbol. So what we are going to do is you just leave out the dollar and you have to see the remaining symbols, whether something matches with our complete RHS or not. So now right now we have only ID. So ID matches with our one of the RHS in our grammar rules. Therefore, we are going to replace with F. Okay, so how does it happen then? So what we are going to do is we are going to pop this ID from the stack, and we are going to push this non-terminal that we are going to use for the replacement. Okay, so ID has been popped and we have pushed F, and still my input remains the same. We are pointing at star now. What we have to do is we have to see what is the next action to be done. Note that only when the RHS complete RHS matches, we are going to perform the reduce action. If that does not happen, then you will have to use shift action only. Okay, so now we'll see whether something matches in our rule. So if you remember the grammar, F can be replaced by T. Therefore, again we can go with the reduce action. So we are going to pop F and we are going to push T. So now we have T, and we have a star pointed to. And if something does not match with this, then we can perform the reduce action. Reduce action will be performed only when something matches. If it doesn't match, then we will proceed with the other action. But sometimes what happens, there may be some conflict. At some point, maybe it is possible to have the reduce action and also possible to have the shift action. So that is actually known as a shift reduce conflict. Means now you have a confusion whether to go with the shift action or the reduce action. As I mentioned, we can use some strategy, and then we can go with that strategy. So for now, what we do is let us shift and see. When we shift, what happens? Star is pushed onto the stack, so it looks like this. So only T star, we don't have anything to substitute. So again, we are going to shift. So now we shifted ID. Okay, and now if you take T star ID, we don't have some RHS like this. We have only ID as the RHS. So we are going to reduce by using this rule, F gives ID. So if you do that, then what has happened now? See, T and star you didn't disturb. Only ID was popped off, and in place of that we have pushed F onto the stack. So now it looks like a T star F is in the stack along with the dollar. So now you have to see whether something matches, whether this handle matches with the RHS. Yes, it matches. T star F is very well there. So what you can do is reduce using T gives T star F. If you do that, you're going to pop all these symbols first, F and then star, then T, and you're going to push T onto the stack. Okay, so now this is the situation, and now we can go by reduce. Have you noticed that here also there was a possibility to go with the reduce, but we have used a shift operation because some strategy has been used. Okay, this strategy only we are going to try out in the technique. Okay, so in some technique we will be using the strategy, and that strategy we are using. Students, please mute yourself. Students, please mute. Okay, so at the line number, that is the step number 4, also we had actually option to reduce, but we went with the shift. Okay, and now we are reducing to E. So in the next step it becomes E, and now because we have arrived at the start symbol and only dollar start symbol is there, and here only dollar is there, we have completed everything, it is accepted. Okay, so this is one process where we have taken this example. So if you notice here, there was a conflict in the step number 4. So you could have even um, reduced T by E. You could have done that. Okay, but we didn't do that. Okay, because if at all you do that, what would have happened? You would have not arrived at the result. Then maybe you will have to try backtracking or something like that. Okay, so that we are not allowing, because if our technique is good enough, then this problem will not come, and also the grammar should be suitable. So that is the thing, like this it works. Anyway, I will tell more about the conflicts, and then we will see how to solve. And according to this example, whatever we took, this example, if you notice, this grammar is left recursive grammar, and we are using it for bottom up parsers. There is no issue if you have left recursion in the bottom up parsers. Okay, you can very well use it as it is. You don't have to change anything. You don't have to remove the left recursion, because anyway we are not using leftmost derivation, so it will not affect here. Therefore the way we are working, the method itself is not like top down parsing. Therefore we can go ahead with the left recursive grammar also. There is no issue in the left recursive grammar in bottom up parsing. So we'll proceed. So next is how does it do? We can generalize also. Suppose my input buffer contains a YZ followed by dollar, and already we have done some actions and something is already there in the stack. Say we have dollar followed by some substring, say alpha, then beta, and then gamma. We have, and on the top we have the gamma. And always whenever you push something, first thing you're going to see is whether some substring matches or not, whether the entire RHS you can replace with the LHS. That's what you're going to see. Now in this situation, suppose if gamma matches with some of the RHS, and if the LHS symbol is a capital B, then we are going to make the replacement, that is known as the reduce action. So gamma is replaced by B in the next step. That is, you have removed gamma, popped gamma, and you have pushed B onto the stack, and our input we are pointing to YZ. Same thing has been represented like this. So gamma has been replaced by B, and then suppose you have Y to be pushed onto the stack. So you will do the shift operation, and then it will look like this. And also suppose if you want to apply now according to this, whatever is shown in this diagram, beta B Y should match with the some RHS there, where A is the LHS symbol. So you can replace that. That's what it means. So beta B Y can be replaced by capital A, and then finally alpha A Z matches with S, so you can replace with s. It goes like that. Similarly, another instance also we can take, here alpha gamma is there, xyz is there in the input, and suppose I have something like this, gamma can be replaced by b. Yes, you can do so. It has been already replaced, and then you push x onto the stack, and then another shift operation, one at a time actually. So y also you would have pushed, say, and then if something matches, you're going to you're going to replace it. Okay, according to this notation, a matches with y, so definitely you can replace this y with capital A, and then you can proceed. Then you have already changed gamma into b, so alpha b x a z will be equal to s, and you can replace with s. That's what it means. It's just an instance, just to understand how the push and pop operations are managed. Anyway, we will take the actual examples later. So it looks like this. So you can easily imagine what can be the handle at each step, and based on the handle you're going to make the replacement. So always remember that entire RHS should match, then only you are going to make the replacement. So that is about the example. Now let us see what is the process and the definition of the reduction process. Here we use the process which is known as reduction, because that's what happens when you make the replacement of some substring by an LHS. That is nothing but the reduction, and our aim is to reduce to the start symbol. So we have to go till the start symbol. So this process is only known as reduction, where it is a process of replacing the substring that matches with the entire RHS of the production rule. At each reduction step, the replacement is done, and it is with the LHS. Okay, so that's what is the meaning of reduction. And also you can see some of the differences between the top down and bottom up. Already have told, it starts from the root, that is the start symbol in top down. Bottom up starts from the sentence and goes towards the start symbol. Here the process is known as derivation process. Here it is reduction process. In the top down it is leftmost derivation. In the bottom up we use rightmost derivation in reverse order. And intermediate results in top down is left sentential form, and here it is right sentential form. A top-down parsing is also known as generate match parsing, because the nature of the algorithm works like that. Means we generate something and we see whether something matches. If it matches, then we pop. It's like that. So that's why it is also known as, but it's not very common name. It is known as a generate match. For the bottom-up parsers, it is a very popular and common name, which is shift reduce parsing. Due to the actions, we call this name shift reduce parsing. And some of the examples for top down is recursive descent parsing and LL of 1 parsers, and even you can take LL of k. Similarly, for bottom up we have operator precedence parser, LR of 0, SLR, LR of 1, LALR of 1, and so on. Even you can take LR of k, LALR of k, something like that. So that is a difference. I have told many times, so I'll go fast here. Okay, now let us see what are the kind of conflicts that are going to occur in the shift reduce parsing. Basically, there are two kinds of conflicts: shift reduce conflict and reduce conflict. The shift reduce conflict is, as the name itself says, you have a confusion in deciding whether you're going to go with the shift action or reduce action in the next step. Okay, so what is the situation? Okay, you can see this example. Statement gives if expression then statement is one option, and the other option is if expression then statement else statement. And okay, some other RHS are also there. And now suppose we have something like this in our stack. You have a lot of symbols, and suppose in some substring, say if I have if expression then statement, and in my input I am pointing to else now. Okay, so now there is a confusion for you, because this particular entire RHS matches with the first option of my production rule. I can go with the reduction, so that is possible. And the other choice is, because we are pointing on else, there is also a chance of performing the shift action. So this is known as shift reduce conflict. Means I can go with reduce action because entire RHS matches. That is one possibility. And the other possibility is that I can even shift else and then continue. So that is also possible. So this particular conflict is known as shift reduce conflict. Okay. So coming to the next conflict is the reduce conflict. This conflict is about you are going to perform the reduce actions only, but using what rule matters. Whether I'm going to reduce with rule number 2, or whether I'm going to reduce with rule number 5 or 6 or whatever. So suppose I have confusion between two rules, whether I'm going to reduce by using rule number 3, or whether I'm going to reduce using rule number 5. Some confusion if we have got, then that is known as reduce conflict. So I have an example for that also. You don't break your head for entire thing. We will just concentrate on where this kind of conflict can occur. Now, if we see in the stack, we have something like this: id open parenthesis followed by id, and now I have comma. Okay, and then id is there, close parenthesis, something is there, and dollar. Okay, so now if at all I want to perform the reduce action for id, because id is there on the top, and if it matches properly, then I should go with the reduce action. So when I want to perform the reduce action, you'll go back to your rules and see which rule you're going to apply for the reduce action. So if you notice, I have highlighted using red color. So there are two possibilities. Parameter also can be replaced. That is, parameter gives ID, and there is one more possibility that expression also gives ID. So now this is one rule and this is another rule. Both are having the same RHS ID. So now if I have to replace this ID with the LHS symbol, do I replace with parameter or expression? That's what is the confusion now. So if I replace with expression, something else will happen. We have to see that. Or if we replace with parameter, what happens? We have to see. So here at this stage, if I want to perform the reduce action, that conflict occurs, whether to apply this one or this one. Okay, that is a confusion. Maybe you look ahead many symbols, and then if you decide, yes, you can do that. But anyway, we will have to use some strategy. Later, I will tell about the strategy. So this particular situation is known as reduce conflict. So you have decided to reduce, but the thing is which rule you are going to use for reduce, because there is a confusion. How do you solve that? So that itself is known as the reduce conflict. So we will take more about it. Now let us see what is LR parsing, and which are the different techniques that are coming under this class. Okay, so LR parsing means, as you know, that the L stands for left to right scanning. That is, the reading is always from left to right, and R stands for the rightmost derivation in the reverse order. The rightmost derivation in the reverse order. And if at all you use the brackets like this and put some number, so that means that is the number of look ahead symbols. Here also we will be using some look ahead symbols. If it is 0, then we don't use the look ahead symbol. If it is 1, then we are going to use one look ahead symbol. 2 means two look ahead symbols, and so on. Okay, and later we will see that the strength of the algorithm, it depends upon also the number of look ahead symbols. Okay, so that we will see. And why we have to go with the LR parsers? Definitely we have got lot of advantages. First thing is that it is having the table form. Once you construct the parsing table, it becomes very easy for you to decide what has to be done, means which action to be taken, whether it is the shift action or the reduce action. It becomes easy for you once the table is constructed. So that is the biggest advantage, and it can be used to recognize all the programming language constructs. And this context free grammar itself is very popular because of the nature and the syntax used. All the programming languages constructs, whatever construct you take, that can be represented, and such grammars can be useful in the parsing, because we can easily verify the syntax using the LR parsers. So that is the second advantage. And then we don't have backtracking to be handled here, because we will have to use some other strategy. We don't have to backtrack and then do something, because we know that if you use backtracking, then it is not efficient. It is as good that you are not taking a wise decision, and therefore you are going back and then repeating the steps. That we don't want. So it is a non backtracking technique. So that is another advantage. It can detect a syntactic error as soon as it is possible to do so. Means it need not wait for the entire thing to be completed. As and when in whatever line it finds the syntax, it will immediately give the error, and it will proceed further also to find the next error. So that is another advantage. And the class of grammars what we can use to construct LR parsers are the superset, and later you will also realize that LR parsers have got wide applications, because LL of one we have seen some examples, but it has its own limitations also. As you all know, that left recursion removal is required, and then left factoring is required. The way we do parsing also, it is little different. But coming to the LR parsers, they are very strong, and you have lot of classes still. It's not just LR of 0 or LR of 1. We have the variations also into it. So that is the advantage, another advantage compared to top down parsing. Okay, so all these makes the bottom up parsers very effective. So let us see what how do we construct these LR parsers. So there are some basics which is very common for all the parsing techniques. So first I will tell something about the item. Okay, and there are a lot of parsing techniques, and one such parsing technique is, say, LR of 0. LR of 0 means because the 0 is there, we are not using any look ahead symbols. Okay, and when you are not having any look ahead symbols, we have the representation of the item also. Item means nothing but something like this. This is called item. Okay, I will first explain and then we'll proceed. Suppose you have some rule like this: A gives XYZ. This is the rule. Okay, and now we have to see, we have to track how the input is taken, and then how the transitions takes place from one state to the other state. Okay, we are going to use the transition diagram here also, like how we used DFA for our scanning step. We have used here also, we'll be using the DFA, but along with the DFA we'll be using the stack also. That's the difference. So if at all we have the rule like this: A gives XYZ, and if you observe here, there is one dot. There is one dot. Okay, so this dot is used to represent the position of the parser. I will repeat, a dot operator is used in the RHS to denote the position of the parser. Means when I say A gives dot XYZ, my next symbol to be read is what? X, capital X. In the transition diagram, my next eligible symbol to be read is what? X. Now, after reading the X, what happens to the dot? It will be moved. So, if you observe here, dot has been moved to the next location. So, once I perform some transition, after reading X, I go to some state. In that state, if I have to continue further, what I do is a next symbol I have to read. So, how do I see that which is the next symbol? This dot operator will help you. Okay, so dot operator will be present before some symbol, and that symbol, whatever comes after the dot operator only, should be read in the transition diagram. So y has to be read. After reading y, what happens to the dot? It will move further. So now z is eligible for reading. Okay, z we are going to read. What happens now? Now dot has been moved in the rightmost position. Means we don't have any symbols after this. Now at the LHSA, for the LHSA, my entire RHS has been processed in my transition diagram. It means that. So once I process the entire RHS and dot is in the rightmost position, this is eligible for the reduce action. This is eligible for the reduce action. Whereas here I can't do the reduce action, here I can't do the reduce action, here I can't do the reduce action. Only here I can perform the reduce action. So I think now we have got an idea of what is dot operator. It indicates the position of the parser while reading. And this kind of notation is known as LR of 0 item, and that's how we represent the production rule along with the dot. So it is not just the production rule. Now you are going to specify using the dot operator also. So like this, we will have some items, and all these items can make a set and that set only we are calling it as a state. Okay, I will give the definition of state now. LR of zero state is what? LR of zero state is nothing but the set of LR of zero items. Okay, if I want to take LR of one items, then that state is known as LR of one state. If I use LR of zero items, then that state is known as LR of zero state. So generally we say states are nothing but the set of items. If at all you are very particular about the parsing technique, and that particular item will be used and that particular state will be recognized. So that is the meaning of state and the item and the dot operator. Okay, so as we proceed, you'll understand more about it. What are the steps? So we are dealing with the first technique, that is the LR of zero parsing technique, and these are the steps. These are very common steps, and almost in all the parsers will be using these steps. So first step is augment the given grammar, and the second step is you can label each production rule by using some number, like as we have done in the top down parsing. That will only help you to recognize, okay, which rule we are using for reduce, which rule we are using for something, or where we are shifting. So to know that only we use these numbers. Anyway, for reduce action it is required, because which rule we are going to apply is important, so that numbering is required. So that is the second step. The third step is construct the state diagram. It is also known as DFA, and we are dealing with LR of 0. So we will be constructing the DFA for LR of 0. Means our DFA should contain only LR of 0 items. So that is the third step. And after the construction of the state diagram, the same thing we can reflect it in the table also. So the fourth step will be LR of 0 parsing table construction. So that is the fourth step. And the fifth step is you can always verify whether your string is working fine, and now you can make use of the stack and then parse. So you'll be using the string parsing, and you will make use of the table which you have already constructed in step 4. So using the table, you can make all the decisions which action to be performed, and you can process and see whether it is accepted or rejected. So that is the last step. So that is these are the steps involved in LR of 0 parsing. Okay, so now let us define what is LR of 0 grammar. You know how the table looks like. In the LL of 1 we have seen how the entries are made. Here also some entries will be made, only the rows and columns I will define later. LR of 0 grammar is what? A grammar is said to be suitable for LR of 0 parsing if at most one entry exists in the parsing table. Okay, so I will repeat. When you construct the parsing table, if at most one entry exists in the parsing table, then we say that the given grammar is suitable for LR of 0 parsing. Okay, so then what can happen in the table? So if at all you have the conflict between the shift and reduce, then both entries will be there. There will be entry for shift as well as for the reduce. So that is the conflict. Means there are two entries now. Similarly, if you have reduce conflict, maybe there are two entries, reduce using rule number 2 and reduce using rule number 3. So both R2 and R3 will be there then. So that is two entries now. Then we can't call it as the grammar which is suitable for LR of 0 parsing. So if at all it has to be suitable, then at most one entry should be there in the table. So that's what we are going to check. If the conflict occurs, then more than one entry will be there. This algorithm I'll come back, because it's better to have the example and then come back to these algorithm, then only it will be clear for you. So I'll straight away go to how to construct the LR of 0 item sets, because anyway these steps, you know, augmenting the given grammar you know very well, labeling also you know very well. So now let us see how to construct the diagram. Let us take the augmented grammar. So first step is done, and then we use something called closure of item sets. Closure of item sets, and we use that algorithm whatever is shown in the previous slide. Let us see how it has to be done. So this is my grammar, the same grammar whatever we took. E gives E plus T, or T gives T star F, or F, and F gives E within parenthesis ID, and after augmentation we have got E dash equals E dollar. Okay, and this one augmented grammar rule, we are going to use 0 as a number usually, and others you can start with 1, 2, 3, and so on. Okay, I have missed one number here, sorry. I don't know how I missed. Okay. Anyway, this one is rule number 4, and this is 5 and 6. Maybe only in this slide it has happened. Later I would have corrected. That is the numbering we are going to use. After this, what you are going to do is you are going to construct the state diagram. So to construct the state diagram, how do you start? Always you are going to start with this rule. That is the first rule being the augmented grammar rule. That is the rule number 0. Okay, how we are going to start? You are going to start like this. E dash gives dot e dollar. Okay, E dash gives dot e dollar. That is why here it is shown. You are going to start with this, and you are going to find the closure of this. Okay, what is closure? I'll explain now. And I naught is nothing but the state number. So you can also very well label the state numbers because that is required to make the entries in the table later. Therefore, you will have to label all the states and use the unique names for the state, and use the continuous names also. Okay, continuous numbering. What do we do now? First thing is that we are going to start with the first rule, that is e dash gives dot e dollar. Okay, why did I use dot? Because I am representing using LR of 0 item. So dot e dollar. Now, I started only with this. All this how we wrote, it is because of the closure. Then what is the meaning of closure? Closure is nothing but whenever the dot appears before the non-terminal. Whenever the dot appears before the non-terminal, then you are going to expand all the rules related to that non-terminal. So in this case, I have dot E. Dot E means I am going to expand all the rules with respect to E. So what is that we have for E then? So for E, we have something like this. E gives E plus T. So I can't just write E gives E plus T. I will have to put dot in the beginning. Okay, because I'm processing now only. I've started processing. This is state number 1, means dot is in the beginning only. So E gives dot E plus T. I expanded this. Then the next possibility also we are going to expand, that is E gives dot T. Okay, so how did I get these two? The rule number 1 and rule number 2 I wrote here because of the closure of this particular rule in this state, and I expanded E. Now do we stop? No. Why? Because you have to see whatever I introduced now, whether it is having the dot before the non-terminal once again. So now dot E appears, or E already E has been expanded. So I don't have to repeat once again. So that becomes duplicate. You don't have to create duplicates. So E is already expanded. So I'm going to skip this. Then coming to the next rule is what? E gives dot T. T is also a non-terminal. Because T is a non-terminal and dot is before the non-terminal, I need to expand even T. Okay, so what are the rules related to T? Go back to your grammar and list out. So T gives dot T star F. Similarly, there is another option, T gives dot F. So I also included the rules related to T. Why? Because of the expansion of T. Now, did we finish? No, we have to see still whether something new has appeared or not. So dot T appears here, and already I have expanded T, so no need to worry. Go to the next rule. Now here dot F appears. When dot F appears, what we have to do is we have to even expand F also. Means we have to list out all the items related to F. So what is that? F gives dot open parenthesis E close parenthesis, and similarly F gives dot ID. Now you see anything is left. E I have expanded from here. E T I have expanded. F I have expanded. Anything is there from here newly? No. So how does it stop then? In a particular state, when you repeatedly find the closure and there is no change in that state, then you are going to stop the process. Otherwise, till then it is a procedure. If till there is no change, you are going to do the iterations. Okay, repeatedly you are going to do it. And once there is no change, then you are going to terminate the iteration and then continue with the next step. So now this all is in what? In state number 0, that is I naught. Okay, so how did we start? This is common for all the problems, students. We are going to start with the zeroth rule, that is after augmentation, whatever we have got that rule, e dash gives dot e dollar. I started with that, and we are going to find the closure in this state. Therefore e should be expanded because dot is appearing before the non-terminal, and once I expanded, I got dot t, and t also was expanded, and then after expanding t, I got dot f, then f is also expanded, and all have been listed now. This is the end of the first state. This is known as closure in a particular state. So every time when you find a new state, you will have to find the closure. Whenever the dot appears before the non-terminal at any state, you're going to follow this procedure. Okay, so we'll see more on this. This is an example. Okay, here also I didn't label properly. Okay, so please, maybe I can correct it. So this is rule number 4 and rule number 5. So these are the rules. Okay, let us proceed. The first state, how to form, I have already told you. After finishing the first state, the next step is what? I have to take a transition. Before that, okay, I will create some more states and tell why it is known as DFA. What we have to do, you see here, I told you about the dot operator. What is the dot operator? It decides, it indicates the position in the parsing, and also it shows which symbol to be read next. Okay, in the diagram, my next symbol to be read is what? From the rule number. Okay, this first rule, what we have is E to be read. So when I read E, what happens? Here I read E dash gives E dot, here dollar is there, you can imagine dollar, and anyway it is the end. So we are going to stop there. Okay, we don't process. So from this rule what we got is, from this rule what we got is, we will have something like this, something like this. After the transition, after reading E is present where all you have to see. It is not just in this rule. Wherever E you are going to read, all that you have to take into consideration. Once I read E, I have what possibility? One possibility is that from this rule E dash gives, when I have read E, then the dot is also moved. It becomes E dot dollar. Okay. And then the next thing is what E gives. Dot E plus T is also there. Here also the symbol to be read is what? E. So you're going to read E, and what happens to the transition? After the transition, the item looks like this. E gives E dot plus T. Okay, and in this state also, whenever you take a transition, after the transition, if at all the dot appears before the non-terminal, then you have to find the closure. Okay, here also we are finding the closure, but here in this particular state, I1, there is nothing like that. Means we don't have anything to be expanded. Okay, we don't have anything to be expanded, because this is a dollar symbol, which is a terminal symbol, and this is plus symbol, that is also terminal symbol. So I don't have to expand more here, and that is the end of it. So we have finished. Maybe if at all you're writing, you can tick the first one is done and the second one is done now. Okay, now what is the next thing then? According to the rule number here, according to the third rule in this state, so what is that we are supposed to read T. So how does it happen then? So we are going to read T, and then we are going to take a transition. And how does it look? I am going to label it as I2, state number I2. And after reading T, what happens? E gives T, dot is going to generated. And similarly, here, according to the other rule, here also we are supposed to read T only. So what happens? T gives T dot star F is what we are going to get. Now again notice that after dot here we don't have anything. So what does it mean? It is eligible for reduce action. I told you, no, if the dot operator is present in the rightmost position in the RHS, it means that you have completely processed that particular rule, and then therefore it is eligible for the reduce action. So E gives T dot is eligible for reduce action, whereas the other one is still not completed. And what is the symbol to be read next is a star, and it is a terminal symbol. Again, in the state I2 also, I don't have anything to expand, so I stop here. So that is that. Then what is the next option? Okay, f is also there. I will show it later. If you read open parenthesis, what happens? If you read open parenthesis, it is like this. So I read open parenthesis, I moved the dot after the open parenthesis, then we got e close parenthesis. Okay, so why is that all these rules are coming? Because of the expansion of e. So because dot E is appearing, you will have to find the closure now. You're going to expand all the rules related to E. And how do you start? Always whenever you expand, you're going to have the dot operator in the leftmost position. Means the first symbol to be there in the RHS would be dot. So E gives dot E plus T. Then E gives dot T. Do we stop? No, it is an iterative procedure, right? So once I get this, E also have to expand, already it is there. Now T also have to be expanded. We expand T. Once we expand T, what we get is we need to expand even F. So all these came into existence now. So just because of this dot E, we got all the items listed here. Okay, so this I wanted to show because this is little complex, means you have to understand, you should not forget. If you forget, then everything will change. So you have to verify at each state whether the closure is required or not. If the closure is required, you will have to list out all the items, expand everything, and then there is no change, then you can go ahead. Okay, so anyway, I will show it completely now. So first state is done, second state is this, third state is this, which I showed. uh, I3 is this after reading F. Okay, after reading F. And I4 already I have explained. And I5 is after reading ID. Okay. So the placement of the states is like this, because just to make it comfortable to fill the remaining part. That's okay. You can write it properly. Only thing is the visibility should be good. That's it. So here again, you can imagine dollar. So these are the states at the first level we have created. Okay, is there any doubt with respect to this student still here? Means from the start state, that is I naught, till you created I1, I2, I3, I4, I5, only till here. If you have any doubts, let me clarify. Otherwise I'll move on to the next state. So we have done I1, I2, I3, I4, I5. Okay, so now again the dot operator will decide what has to be read next. Okay, so now what happens here? According to this rule, E dash gives E dot dollar. In this, what has happened? Do I have anything to read now? No, because I have reached the dollar symbol. Dollar symbol is nothing but the end of file marker. Therefore, I would have reached the end of my parsing itself when I reach this. So what you can say is it can go to the accept state. So it can go to the accept state. So that is the meaning of it. So ACC means it is accept. So that is about this rule, first rule. Coming to the second rule here in this state, E gives E dot plus T is there. Means what is the symbol to be read next? The symbol to be read next is what? Plus. So I am going to read plus and see what happens. So I am going to read plus, and what happens to my next state? It is this state we are going to get. What is that? E gives E plus. So you have to observe the dot has been moved after the plus, after reading plus. So dot T. So this is what we are going to get. And if you stop there, then it is not the complete state. You will have to find the closure in this state. So because of this dot capital T is a non-terminal. You have to expand T completely. So all the rules related to the T you have to expand. And then because of this dot F, you also have to expand F. And while expanding, notice that dot is appearing in the leftmost position in all the rules. It's like starting from beginning for that row. It's like that. So I6 is created now. So I6 we got from I1, and that is a transition after reading plus. Similarly, if you go to the state I2, what is that I2? We have the first rule, which is E gives T dot, means this is eligible for reduce action. I don't have anything to read from here because already dot is in the rightmost position. It is only action to be taken is reduce now for this rule. Whereas the other rule is having something to be read, where star is the symbol to be read. So let us read that symbol. If I'm going beyond the time, let me know. Okay, 5 more minutes. Okay, I will complete one more state or two more states and stop. We have to read this star. So once we read this star, what happens? You're going to get something like this T star dot F, and because dot F is appearing, F you're going to expand. So only F, all the options you're going to expand. So that is the state number 7, that is I7. So coming to the state number I3, if you observe already dot is present in the rightmost position, this is also eligible for reduce. I don't have to do here anything, so I'll skip that. And going to I4, already have explained how it works. Here I need to read some things. So what are the things to be read then? I can read E, I can read T over here, I can read F over here, I can read open parenthesis, I can read ID. Okay. And whenever you are creating a new state, students, you have to remember that if it is going to generate the same state, then you can reuse the state. You don't have to create the duplicate states. If something similar to this is going to be created once again, then I don't have to create once again. I can reuse the state, say I4. For example, when I read open parenthesis over here, see, you can see the self loop, right? So when I read open parenthesis, what we are going to get the result is nothing but F gives open parenthesis dot E close parenthesis. Because of the dot E, I have to expand E. Because of this dot E, I have to expand T. Because of this dot F, I have to expand F. So I'm going to get the same contents. Then what I can do, I can reuse that state. So that's why it is a self loop. On open parenthesis at I4, it is a self loop. So similarly, when I read ID, I already have a state with the ID, right? So I can reuse the state. So when I read ID, I can go back to I5. When I read F, I can go back to I3. But only when I read T, what happens? If it is something new, you will have to create it. Okay. So if I read T, also I'm going to get something. Let us see that. Um, if I read T, what happens? I will get something like E gives T dot, and then T gives T dot star F. That's what I'm going to get. So if that state already exists, I can reuse it. Similarly, when I read E, if something different I'm going to get, then I'm going to create a new state. So E gives E dot plus T, we are going to have. And similarly, one more option is also there for E. So this is one option, and other option is that here. So F gives E, first rule we are going to read E, and in the second rule also we are going to read E. That's why anyway it is put in the reverse order. That's it, no problem. Anyway, it is a set only, so it's okay. E gives E dot plus T, and the other one is F gives open parenthesis E dot close parenthesis. So what you have to remember is whenever we take a transition, the dot is also moved. So, and which you are reading matters, and you are going to see that. Similarly, here also we are going to create, not much time, I think. Maybe we can stop. Okay, I will just give a reason why we are calling it as DFA. We are calling it as DFA because the property of the DFA is satisfied. The first thing is that for any symbol, I don't have multiple moves. See, if when I'm reading E at this state, I have only one move on E. Similarly, when I'm reading T, I have only one move on T. ID or whatever you take, there is a unique move for any symbol, whether it is non-terminal or terminal symbol. So that matches with the definition of the DFA. That's why we call it as DFA here. Even though DFA cannot handle everything, but remember that we are not just writing the state diagram. Only with this we cannot complete the process. We will be depending upon the stack also. Therefore, using that stack and then creation of the state diagram, which is also known as DFA, we can do so. So that's why we call it as DFA. There is no issue if we call it as DFA, or we say state diagram many times. So this problem I will continue in the next class, students. Maybe you can read once, already it has been uploaded, this PPT. You can read once, and if you have any doubts, let me clarify in the next class. Okay, students, thank you. Already it's time. You can leave.